there's a test, that you can do, a physics test, to tell what frame of reference you're in, okay? You just drop something. It's called the floating ball test, okay? You just hold something out, you drop it, see what it does, okay? And this is the two things that everyone knows about frames, right? Things accelerate to the ground in an accelerating frame. Things stay inertial in an inertial frame. See how they never call an accelerating frame a non-inertial frame? That's stupid. It ruins these two sentences. These two sentences are this way because they make sense. All inertial frames of reference have the same physics laws. See, an inertial frame is a frame that has the simplest physics laws. So that's how they do it, right? They define an inertial frame as something that has the simplest physics laws. But the funny thing is that there's really only one thing that makes physics laws complicated. So they really break them up into two categories. Inertial frames have no acceleration. Accelerating frames have acceleration. These are your two types of frames. You have frames that have acceleration, they're called accelerating frames. And you have frames that there's no acceleration. We call them inertial because everyone keeps their inertia. I want you to keep in mind, gravity equals acceleration. They are the same exact thing, okay? Acceleration is acceleration, right? Gravity is a specific type of acceleration. So you can either use acceleration, right, by accelerating you and creating your own gravity, right? Or you can use a planet to create your own gravity, right? But the thing is no matter what gravity machine you make, whether it's a ship with rockets, a spinny thing that rotates, or a planet, each one, no matter what gravity machine you use, you have to be touching it. You can't just be floating there, okay? You can't just be floating there, okay? You have to be touching the gravity machine. Whatever's making the gravity, you got to be touching it, okay? Three types of gravity machines. First type, rockets, right? This rocket machine is a gravity machine, okay? It accelerates upwards, okay? And when it does that, the floor and you, right, that's attached to the floor, relative to you, okay, between space-time and that floor and you, okay, relative to each other, you are accelerating at 9.8 meters per second squared. To drop things, like this ball right here that's just floating there before he starts his rockets up, drop things, accelerate, and get stuck to the ground relative to the man, okay? But the ball is inertial, okay, until touching the ground. He's just floating there, right? He's just floating there, waiting the floor come up to accelerate him, right? So he's just floating relative to space-time, this ball, right? This ball down here, it's accelerating now. It's in an accelerated frame of reference. Here it's in an inertial frame. Same exact thing here with number 2. This gravity machine is a spinny thing. You can see it's rotating around, spinning around, right? Guys, this is the floor. This is the ground. The outer circle is the ground, right? Okay, everyone's stuck to the ground, just like here. The ball is stuck to the ground. Over here, so I want you to show you. If you have a ball here and you just drop it, it'll go along this tangent line again. But when he drops that ball, it's going to go straight down here. But see, the thing is spinning, right? And it spins at the same rate so that the ball will be caught right here, okay? So relative to in the man's frame of reference, the ball is accelerating down. But the ball is basically just going constant speed, straight path. It's being inertial. Just like here, right? It will stay inertial. It will be just like up here. This ball is inertial, okay? Until, remember, standing still and moving at constant velocity, same thing. He is same here. This guy has a constant speed. If he drops the ball, it's going over this way, right? Straight line, constant speed. But, just like this guy would be inertial too. This ball's standing there, right? Until the ground hit it, right? So while the ball was dropping, it is inertial until it hits this bottom plate, right? But The man, right, if there was a man on here spinning around, he's in an accelerated frame, so he sees the ball as accelerating towards the ground, just like this guy on here. Both these guys, when they drop a ball, they think that the ball accelerates down, and in both cases, the ball is not accelerating at all. It's still inertial. Okay, so what's your third type of gravity machine? Okay, your third type of gravity machine is called a planet. Same things apply. Everything's the same, right? Everything's stuck to the ground, just like on all these gravity thingies, right? The ball is inertial. Okay, the falling ball, just like here, falling ball, inertial, falling ball, inertial. This ball is inertial as it falls because it keeps its spatial coordinates relative to space-time as space-time accelerates down to the Earth. This ball is inertial and stays inertial because relative to space-time it is not accelerating. It's this floor that keeps accelerating in or up. Same here. Ball. All three cases the ball is just floating because relative to space-time the ball is not moving. It's just floating in this, all situations. And drop things accelerate and get stuck to the ground relative to the man on the ground, just like here. Even though the ball is inertial, the man, relative to in the man's frame of reference, same here, they see the ball as accelerating, right? Same down here, right? The ball is inertial until it touches the ground, right? It's just floating relative to space-time. See what's happening here? This machine that creates gravity, right? It accelerates the ground relative to space-time. This machine here, and it does it by changing the speed, right? Velocity is two things. Speed and changing. Velocity is speed and direction. So if you change your speed or your direction, you're accelerating, right? This guy does it, right? 'Cause accelerating and gravity is the same thing. Acceleration creates gravity, is basically it. So they accelerate the floor, create the gravity. They accelerate they change it, keep changing the direction, right? Changing their velocity. That means they're changing they're accelerating. This creates the gravity, right? Change of the speed, change of the direction, both acceleration. Okay, you're accelerating the floor. Here, the same thing, but instead of accelerating the floor, right? You're accelerating space-time down, right? The planet, it can't move, right? It's stationary, right? So relative to the man, even though he's stationary, the space-time is accelerating through him at 9.8 meters per second squared. Okay? So that's where you get your acceleration. That's why you're in an accelerated frame, because relative to space-time, you're accelerating. In all these things, that's what makes you an accelerated frame. Because you in space-time, whether it's space-time or you, someone, okay, relative to each other, yins are accelerating 9.8 meters per second squared, or whatever the acceleration is. Now, a lot of people say the gravity here is real gravity, and this is simulated gravity. I mean, gravity is gravity. Gravity just means that you have inertia, like the balls. Okay, the ball here, and something, whether it's a planet, a spinny thing, or this ship, is making you accelerate relative to, space-time. You know what I mean? When you touch the ground, you're accelerating. When you touch the ground, you're accelerating. When you touch the ground, you're accelerating. All three frames, as soon as you touch the ground, you're accelerating. When you're in free fall, you're inertial. All three frames. So it's easy to see, get a magic marker, get a ball. Things accelerate to the ground in an accelerating frame. Makes sense, right? Things stay inertial in an inertial frame. Okay? Now there is another type of accelerating frame. There's a bunch of accelerating frames. It depends on how you categorize them, right? There is one called a relative inertial frame. And you might say, well, why are they calling it relative inertial if it's an accelerating frame? Well, because it's like this man on the Earth, right? Both of them are in an accelerated frame of reference, but they're in the same... See, inertial means you're standing still, right? Or you're moving at a constant velocity, right? See, they're relative to each other, the man and the Earth's surface, they're standing still, right? So, and they have the same physics, So that's like, inertial, all inertial frames have the same physics laws, you know what I mean? So that's why we call it relative inertials, because relative to each other, they're kind of inertial because they're standing still, they share the same physics, but they're not really inertial, they're accelerating frames. But relative to each other, they're kind of standing still. The physics is the same is what's important. Same here, if you have a man on the ship, both the man and the ship are in the same frame of reference. Just like this guy. He's in the same frame of reference. This guy's in the same frame of reference as this machine. That's why they're all accelerating. It's the accelerating frame of reference. But see, these would be, this man and the ship are relative inertial to each other. This man and the spinny thing, relative inertial. This man and Earth, relative inertial. But that means two frames that are both accelerating at the same rate. In accelerating frames, things get stuck to the ground. Things accelerate to the ground. If you were inertial in outer space, you'd be just floating. The ball would just float, right? All these things have the same thing. The ground forces people or a ball or whatever to deviate from their inertial straight line geodesic path, right? See this ball? It's just falling. It just stays inertial. It's just following the geodesic, the straight line, so it's inertial. But what about the ground? The ground is not following this red geodesic path. The south isn't, neither is the north, otherwise it would get crushed. The space-time is accelerating down. This red line is the same spatial coordinates. This red line is the whole red line is the same spatial coordinates. So if the North Pole and the South Pole wanted to follow their straight line geodesic inertial path, they would follow the red path, but they don't. They can't. So they stay still because space-time. So what is accelerating then? If it's not the ball, technically it's not the surface of the planet is just looks like it's just standing there. What is accelerating? The space-time. This is the spatial coordinates. It's accelerating to the center of the Earth. So relative to the space-time, the surface of the Earth is accelerating. You can see it each hour or each unit of time. It accelerates. That's the thing. It doesn't matter if you accelerate or space-time accelerates relative to you. It don't matter. It's the same thing. You have gravity and you have all this other, physics laws. It is an accelerating frame if you are accelerating relative to space-time. Don't matter if space-time is accelerating through you, like gravity, or you are accelerating through space-time like a spaceship or a spinny thing. It don't matter, okay? That's why they call it relativity, okay? Counts as the same thing. You are in an accelerated frame, okay? If you're accelerating through space-time, you're in an accelerated frame. I can't say it. It doesn't matter who's doing the accelerating when it comes to this. It can be the space-time or you, but you can obviously see geometrically the surface of the Earth is accelerating up relative to the space-time. That's why it's an accelerated frame of reference. However, the ball follows the red geodesic path. Okay, see this red path is the inertial path, and it can't go on its inertial path, so therefore it's being accelerated relative to space-time. Now I want you to keep in mind, this spinny thing, you can have one that goes 9.8 meters per second squared. You can have an infinitive number of these at different sizes, right? Same here. You can have a million types of these ships, all going at 9.8 meters per second squared, different sizes, all over the place. Infinitive number of these, 9.8 meters per second squared. All the physics line up with this. So obviously it's an accelerated frame of reference. And this floaty man, you can think of an infinitive number of, places out in outer space where you can float around, you know what I mean? There's an infinitive number, and none of their physics matches up with the physics on Earth. So obviously this is inertial, this is not, right? These are accelerating, they match up. This is accelerating. You can see the ground is accelerating. You can see it geometrically, mathematically. You have the floating ball test, so you have actual physics experiments proving it. And you have common sense. If everything in your frame is accelerating, then you're in an accelerated frame. You can use common sense.